Today I'll talk about mathematical basis of support vector machine. This lecture is part of my series of lectures on machine learning. So I'm sorry for the quality of this diagram. If let us say there is a binary classification problem with minus samples and plus samples. So these are points in this two-dimensional space, and let us assume that there is a plane which perfectly separate these two samples. If yi is equal to +1 for samples which are plus, and yi is equal to -1 for samples which are minus, then yi multiplied by dot product of these two vectors plus b is more than equal to 1, because this hyperplane is dot product of these two vectors plus b is equal to 0, and this vector w is perpendicular to our hyperplane, which is perfectly separating these two group of points, and b is the offset. So if yi multiplied by this is more than or equal to 1 for perfect separation, then yi multiplied by dot product of these vectors plus b minus 1 is 0 for points which are in gutter or which are in this street. So what is the width of the gutter or width of this street? For optimal separation, we aim to have a widest width of this street. So if there are these 2 points x minus and x plus, and there are these two vectors, and the difference between these two vectors is x plus minus x minus, and if we multiply it by the vector w, which is perpendicular to our separating plane, divided by the magnitude of vector w, then this will give us the distance between or the width of this gutter or street. So if we solve this, then we get that this width is equal to 2 divided by the magnitude of vector w. So our objective is to have a maximum width or maximum width of the gutter or street. So we need to maximize this quantity 2 by magnitude of vector w, or we can maximize this quantity, or we can minimize the magnitude of vector w, or we can minimize the half of square of the magnitude of vector w. But the constraint here is, as we have seen in our previous slide, this constraint is that yi multiplied by dot product of vector w and xi plus b minus 1 is equal to 0. So this is our constraint, and this is our optimization problem. So let us see what is the method of Lagrange multiplier. So if we have a primal form, an optimization problem to minimize a function, and this is our constraint, then the Lagrange multiplier combine these two in this form as the optimization function plus the constraint, and to solve this we calculate the differential of the Lagrange multiplier and differentiate it with respect to the variable x, which in our case of support vector machine is the vector w, and we set it to 0, and then when we get the value of x, that is vector w in our case, we put it back to this Lagrange multiplier form and we solve it. So this is the method of Lagrange multiplier. So if we do this in our case of support vector machine, we get that this is our Lagrange multiplier form, and we differentiate it with respect to the vector W. We get the vector W as summation of alpha I, yi, and xi. And if we differentiate it with respect to B or offset, then we get it as that summation of alpha I, yi is equal to 0. So we the final equation is that we need to maximize this term subject to these constraints, and the prediction is given by this. So this is very simplified form we get after solving using the Lagrange multiplier. So this was the case for perfect separation. If there is no perfect separation, then we can have a new primal form. We add a slack parameter and a regularization parameter. So we need to minimize the half of the magnitude of vector W square plus regularization parameter and summation of this slack parameter. And we get this constraint. So these are the two equations which are final equations in primal form. And in dual form, we can use the Lagrange multiplier. So now let us see what are the equations and terms which are provided in the documentation of scikit-learn library. So these are the documentations, and this term is very similar to our term. It is noteworthy that this k within bracket xi and x, this is the kernel function. So if the original data is not separable, then we can use the kernel function to get a better separating plane or a hyperplane between the two groups or two or more groups. So then this is support vector regressor from scikit-learn. This is very similar to our equation. Then this is the prediction of support vector regressor from scikit-learn. So what are the kernel functions available? So we have these kernel functions available: polynomial kernel function, sigmoid kernel function, radial basis function, Bessel function kernel, ANOVA kernel. So this is the mathematical intuition behind support vector machine. And these are the very good references. This is online guide, and this is the MIT lecture, online lecture on YouTube. So you can go through these references to get more information in an easy language. So this is all for today. Thank you very much.